Hello and welcome to our February webinar presentation for the Underground Construction Association's Young Members Group. My name is Erin Clark and I am the Professional Development Chair for the UCA Young Members, and I'm joined by Anthony Bauer, the Chair, and Shannon Goff, the University Outreach. I hope by now everyone is familiar enough with our group. If you would like more information on us, you can keep up to date on activities with our group, the events, the webinars, and the scholarships by checking out our website at community.smenet.org/UCAYM. You can also join our group on LinkedIn, named UCA of SME Young Members. This year, instead of the NAT, there will be the World Tunneling Conference, and it's the first time it's held in the U.S. in 19 years. It will be held in San Francisco, California, April 22nd to the 28th. The prices for the conference go up this Friday, so make sure you sign up this week. At the WTC, the UCA members, in participation with the ITA Young Members, are going to be hosting a networking event on Monday night. This event is going to be drinks and food, and come meet other members of the industry that are age 35 and under. We also would like some volunteers to man the booth that the ITA and the UCA Young Members will be putting on throughout the conference. If you are interested in this, please send me an email. My email is listed there at Erin.Clark with me at jacobs.com, or you can reach out to us through our website. And next month, you can meet us again for a webinar. I'm not sure what the webinar will be yet, but check back on our website for more information. And finally, today, we'll kick off with our webinar by Dr. Aydogmus. Dr. Aydogmus is the Director of Technical Services for Flatiron Construction based in Broomfield, Colorado. He also serves as the Principal Design Manager for HOCHTIEF Engineering in Essen, Germany. He has a PhD in Geotechnical Engineering from Freiburg University of Mining and Technology, where he graduated summa cum laude. Tanner has over 15 years of experience in all phases of domestic and international transportation, transit, and complex underground engineering projects, and has authored more than 90 technical papers and articles. Today, Dr. Tanner Aydogmus will be presenting on the design of the Northern Busway Tunnels in Brisbane, Australia. This presentation will focus on the challenging aspects of the project, the analysis methods utilized to deliver the design. Dr. Aydogmus, when you're ready, can you please share your screen?
Hello, everyone. Can you see my screen, Erin?
Yes.
Perfect. Yeah, Erin, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen, dear colleagues. My name is Tanner. I'm working for HOCHTIEF and Flatiron. Before I start my presentation, maybe let me share with you the link between HOCHTIEF and Flatiron for your benefit. So, as you might know, HOCHTIEF is Germany's largest construction company, which operates internationally, and it is ranked as one of the largest general construction companies in the US through its subsidiaries Turner and Flatiron. Similarly, in Australia, through the CIMIC Group. HOCHTIEF Engineering is HOCHTIEF's in-house engineering firm with an international workforce of over 500 employees. It is considered as the biggest construction industry engineering firms, as I'm aware of. It is also worthwhile to mention that HOCHTIEF Engineering provides not only services for HOCHTIEF. I would guess more than half of the volume of the services that we provide is actually for clients outside of HOCHTIEF. Now, coming back to my person, so I'm currently located in Denver. I'm heading the technical services group for our subsidiary Flatiron, and practically I'm providing company-wide technical services throughout the US and Canada. My affinity with this project in Brisbane relates actually to my previous employment with ILF Consultants. As you might know, ILF is an engineering firm with the roots in Austria, and as such, among others, they are known for their expertise in the new Austrian tunneling method. Here, we see an outline of the presentation. So it summarizes the key aspects that I will be addressing in the next 40 to 45 minutes with yourselves. After a short introduction of the overall project scheme, I will be going through with you the specifics of the Northern Busway Tunnel. So this will include the alignment, geologic setting, and site conditions. I believe looking at these aspects is very important to understand the challenges of the project, because the presentation, it will primarily focus on selected aspects of this kind of challenges that we will be touching base. So in this presentation, I will be also discussing analysis methods utilized to overcome or to deliver the design of this successfully completed project in Brisbane. The focal point, I would say, of this presentation lies on the initial ground support analysis and design of a shallow covered tunnel, as it is schematically depicted on the right-hand side. I will explain the details later on. In doing so, I will be guiding you through the complete cycle of the design development. I will be starting from the developing of an engineering geological model. We will look at the evaluation of geotechnical parameters, but ultimately the goal is to look at also analysis aspects, and all of this will be focusing on the near surface tunneling aspects. And the presentation will be closed out with few selected photos from the construction site and a brief summary of the takeaways of this presentation. On this map, we see an overall view of the construction, which includes actually 3 separate projects. So the Airport Link, the Northern Busway, and the Airport Roundabout projects are major infrastructure projects in northern Brisbane. So these projects were developed to address the traffic issues in the Brisbane metropolitan area. Generally speaking, it is a motorway connecting Brisbane city to the northern suburbs and ultimately to the airport in the southeast corridor of this project. The Airport Link, which constitutes the major package of this project, it's delivered by public-private partnership contract. This project includes 6.7 kilometers of toll road, which I would guess maybe 80 or 90% is underground, which is depicted here in this blue line. This contract package also includes 2 further packages, which are delivered for the state government, which are actually a typical design and build contracts. This includes the Northern Busway and the roundabout upgrades at the airport. I will give the details about the Northern Busway Tunnel in the next slides. So we are talking about a road tunnel dedicated just for bus traffic only, and the roundabout upgrade is on the end of this alignment. It includes surface redesign and big overpass bridge structures. The overall value of the 3 contracts was estimated to be on the order of 5.6 billion Australian dollars, and the Airport Link package included a volume of 4.7 billion, so it's a considerable amount of money. The project has started in 2008. The construction works has been completed within 4 years. The PPP project is financed by a consortium called the Bris Connections, which is currently operating the roadways and the tunnels and collecting tolls for a total of 45 years, with the state government paying for the additional busway and the airport roundabout upgrade projects. The contractors of this, I would say, mega project were Thies and John Holland. The designers were Parsons Brinkerhoff and Arup. Both were engaged to deliver the detailed design for this PPP and design build projects. To progress the JV into the detailed design, the design JV has engaged specialty designers, as we see on the right-hand side of the slide. And here you will recognize ILF. So ILF was assigned initially to analyze and to design the initial ground support and the permanent lining of the Northern Busway Tunnel. But during the construction, the scope has been extended to include also design packages for the Airport Link, including on-site services. On this slide, we see the stage 2 portion of the Northern Busway Tunnel. It is a 3-kilometer long 2-lane road way for buses only, and it includes a mine tunnel section. The details of this mine tunnel sections we will see in the next slides. So actually on this slide we see the details. So we see in plan view on the right hand side, also in the cross section, the geometries, the clearance, and the construction sequence of this busway tunnel. The busway tunnel, as it can be seen on the right-hand side, runs from south to north below an major urban arterial road. The horizontal alignment shows an S-curve following the right-of-way underneath the roadway, and it includes the construction of a large low-point drainage sump. I'm pointing it with my pointer, so it is indicated with this gray box. This is approximately the deepest location of the alignment. On the typical cross-section on the left-hand side, we see in blue the busway tunnel, and in red the airport link mainline tunnels, which run in a very close proximity to the busway tunnel with a minimum separation of 5 meters. The busway tunnel has a horseshoe-shaped profile. The crown is very flat, as we can see it from this drawing. The excavated width is approximately 16 meters in width, and the full tunnel excavation height is about 9 meters. The rest of the dimensions can be inferred from this table. And the ground cover, this is a very particular aspect of this tunnel, is that the cover over the tunnel beneath this roadway is approximately at the minimum place 3.5 meters, and the deepest location it can go up to 12 meters. The excavation sequence of the mine tunnels followed the principles of the Neo-Austrian tunneling method, or it's also usually known as the sequential excavation method. The construction sequence is depicted on this sketch. We can see through the numbers the excavation sequencing. In general, the top headings of the mainline tunnels are excavated first and supported, of course, and it followed by the top heading of the busway tunnel. And these were followed by the benches in the same order, mainline tunnels first, followed by the busway tunnel. On this slide, we see the vertical alignment and the geology along the busway tunnel. Let's maybe first focus for a moment on the vertical alignment. So on the south portal is located at the left-hand side, and consequently the north portal is at the other end of the alignment. We see the location of the low point sump, which is the deepest location of the tunnel. So the busway tunnel runs mainly through the lithological units, Narrenvale, Farrenvale. I will talk about it in a minute. Abbreviation would be the NFG, and in blue through the Brisbane TÜV. And the tunnel also passes through a transition zone indicated here in this yellow color, which is located between both of these lithological units. The NFG in general comprises of meta-sedimentary rocks. So mainly we can talk about phyllites. They are in Brisbane quite horizontally foliated. And the group of the Brisbane TÜV can comprise of tuff, conglomerates, breccias, minor sandstones, and shales. The complex group of the transition zone comprises a mixed group of relatively unconsolidated but cemented channels of screed deposits, say small loose rocks. Both formations, the NFG, but also the TÜV, generally have very deeply weathered and variable strength profiles, with many zones, I would say, completely weathered, and they were exhibiting soil-like properties, in particular in the upper zones. And these zones are indicated here with the dashed lines. In particular, in the transition zone, it was anticipated that the weathering will be much deeper. It covers the complete sphere of the tunnel. And in this region, we were also expecting several shear zones and weakness zones, which we in reality encountered. On this note, I just provided you a few selected characteristics of the different lithological units, just to get you a feel about the range, about the phyllites, for example. The uniaxial compressive strength ranges between 10 to 50 megapascals in the upper regions, in the regions where we have the highly weathering, so we are on the lower side, and in deeper sections, let's call, for example, NFG2, would have 50 megapascals. The transition zone depends on what kind of material we are encountering, can vary between 10 to 25 megapascals, and the tuffs in Brisbane in generally have maximum 65 megapascals. Now, moving on with the first challenge of this project. So at the southern portal, the ground and an area about the tunnel is occupied by a large pop fig tree. It is depicted on these pictures. We see on the lower picture the work currently showing the excavation of the portal area at the height of the crown of the tunnel. So the pop fig tree is actually nothing else as a named tree. So this tree was anticipated to be more or less 110 years, and as such, there was a vegetation protection order on it, and it had to be retained or preserved throughout the construction. The arborist reports were reading that these trees in generally have a root structure where the root ball is extending into the ground, I would say 1 to 2 meters. But in this special case, it was reported that this tree found some water sources within the fissured rock. So some of the roots were extending to a greater depth, up to 4 meters, so almost touching the crown of our tunnel. Consequently, at the outset of the project, the tunnel alignment was shifted horizontally and lowered vertically to maintain as much roof structure as possible, and of course to prevent damages to the root ball. I can maybe share with you one situation. The biologist was of the opinion that we are damaging the root ball, and the construction was stopped for, I would say, maybe 1 week until we made or secured and made sure that the tree does get enough water as required. We already heard about the low point sump. So here on this slide, we see an axonometric view and a typical profile at the location where the low point sump meets a niche. As it can be seen by the dimensions provided on the slide, the low point sump constitutes a very large opening by itself. So we're talking about 4-meter depth and 10-meter in width. Together, the niche with the low point sump provides an asymmetric shape of the tunnel, as we can see it on the left-hand side, which constitutes a challenge for the initial support design, but also for the final lining, and it needed to be addressed during the design. So there are actually more challenges on top of the geometrical issues related to the subsurface, let's say existing or future works, but I will get to this one later on. Owing its location being in an urban environment, and of course also being a shallow tunnel, the existing and future structures constituted an additional challenge for the tunnel design itself, in particular for the initial support and final support design. At one location, as shown here on the sketch, the tunnel was driving next to an existing shopping basement, a shopping center basement with less than 3 meters of clearance. This constituted, of course, a challenge for the excavation, but also the initial ground support design, as any excessive deformation needed to be avoided to prevent damage to this existing structure. On other locations, we had also, there were plans for future structures. on this case, as it's shown here, a 7-meter deep excavation is supposed to be excavated upon completion of the construction of the tunneling works, or let's say during the operation of the tunnel facility. As you will imagine, that 7-meter excavation will provide an unloading situation, and it will disturb the stresses around the tunnel perimeter, and this will constitute a challenge for the final lining design. And interestingly hereby is the effect needed to be addressed during the design development. As a summary of the challenges, I would say the key challenges for this shallow tunnel were definitely the low cover over the tunnel beneath a major urban tunnel. At the south portal, the cover was at maximum 3.5 meters. Of course, we have seen also the geology. The geology is very variable along the alignment, and it provides a mixed phase tunneling condition. And the properties of the rock was also ranging from surface residual at the crown of the tunnel to moderately strength or highly weathered rock characteristics at the tunnel face area. As a consequence, the predicted settlement values and their potential to cause damage to existing buildings was very critical in obtaining an approval for the selected tunnel alignment. On this plan view, we see all the challenges summarized, and it gives us an indication of the selected calculation sections in addressing the geological and geometrical challenges of this project. The analysis and design included 2D and 3D computations along with several analytical design checks. So we were mentioning that the construction of the busway tunnel followed the NATM tunneling principles. And on this chart at the center of this slide, the flow chart is indicated for such a process. So in general speaking, we can subdivide this process in a design stage and a construction phase. And we see also in this red arrows that this process is an interactive process. I trust that the NATM tunneling process or the SEM tunneling process is known to us, but still let me just maybe summarize the main aspects and the consequences of it for the design and construction of a shallow cover tunnel. If I would summarize it in very simple words, I would say the intention of the NATM is to activate the strength of the ground, as it is indicated on the sketches on the right-hand side. Basically, the initial ground support will be inserted into ground in order to form a ring-like or an arch-like structure to support the excavation. So we are trying to support the ground to support itself by an arching. So the ground loading, which is acting on the initial ground support system, results in deformations, which we are continually monitoring. And these monitored deformations are compared with predetermined trigger values. This tool gives us the ability in order to continually verify our analysis results, and in cases where we have a deviation, it gives us the opportunity to adjust the initial ground support measures as it is required at the field. You will appreciate that in a shallow cover tunnel, an arching upon which the NATM principles found cannot be fully developed as it would develop, for example, for a tunnel in much deeper sections. And it is quite important for me at this stage to emphasize that the determination of the design parameters and also the tools for the analysis and design which we are choosing must be carefully evaluated or chosen as, I would say, the theories, the known theories or the existing theories are more or less applicable for deeper tunnels, and they are may or not suitable for shallow cover tunnels or only conditionally applicable. But exactly these 2 points, the design parameters and the models, I will be addressing the next stages of this presentation. Let's start the design with the geotechnical model. So on the right-hand side, we see typical bore locks for the lithology of the NFG materials. It represents the classes NFG3 and NFG4. And as with all projects, the borings constitute the starting point to develop a geotechnical model. But we also need to understand that in an urban environment, the accessibility of the ground for ground investigations is quite challenging. Often the best available boring locations are quite in a offset of a tunnel alignment. Let me show it, for example, in an example on this geotechnical model. In this case, the boring upon which the model has been derived is in an offset of 60 to 61 meters away from the tunnel center line. Still, this boring constitutes the basis in developing the engineering model as we see it on this screen. So the varying geological conditions make the interpretation even more difficult. To develop a realistic model, it really requires a good understanding of the local geological history, because we need to rely or combine all information that we can gather together, and we need to have the ability to extrapolate all this data in 3 dimensions. Given all these uncertainties with the effects that we can have in the execution of the bore locks, the interpretation, the offset, etc., and constant iterative process or comparison between the assumed geotechnical models and the encountered ground conditions is a must. And this is one of the principles for the NATM. Here, for example, we see an excellent match between the assumed and encountered ground conditions. On the previous slide, we have seen the assumed ground conditions. This is the encountered ground condition approximately at the same stationing. In the next step, the evaluation of the geotechnical parameters for the design requires a good understanding of the boundary conditions of the tunnel excavation in order for us to describe the likely rock mass behavior types, including the potential failure mechanism. Examples of rock mass behavior types, so I'm talking actually about the reaction of the rock mass to the excavation, are shown in the sketches on the right-hand side. These are some reference project sketches. But when we look at it in detail, so you will appreciate that a blocky material, let's pick the 2 on the upper side, will have a different behavior than a highly weathered or fractured rock. Let's assume this type of behavior type. They have a completely different behavior types or response to the excavation. So we can state that the rock mass behavior type forms the basis for the design of an excavation sequence and the selection of an appropriate design. Hence, the choice of the numerical model may be based on the analysis of the likely mechanisms of both the rock mass conditions, but also the rock mass behaviors. Out of this, the consequence is that the geotechnical parameters will also need to be developed depending on the predominant failure mode. You will appreciate that a highly weathered and fractured rock is will exhibit a stress-induced failure mode. This kind of failure modes will most likely be modeled within continuum analysis, saying we need some parameters in order to simulate a continuum model. In the other hand, if you have a very fractured, blocky rock, this will more likely fail in a block failure mode, and this kind of situations would be likely modeled or analyzed with key wedges or an distinct element method. And here, the discontinuity parameters are more relevant than the mass behavior. Before I go to the evaluation of the geotechnical parameters, maybe let me first summarize the fundamentals of the input parameters, as we need to understand the quality of the input determines the quality of the output. I just summarize here a few points. It is very important that the input parameters should be obtained from laboratory testing, if available, of course. And if you are getting some laboratory tests, usually the starting point is a geotechnical data report. What we need to have to do is we need to check these results for plausibility. If we have some outliers and we can justify it, we should eliminate them. And if the number of tests are sufficient, we should run a statistical model in order to account for an upper, lower bound, or best estimate ranges for the analysis. This plays an important role, in particular, for a low-cover channel, but I will discuss this in the next slides. It's also important for me to emphasize that an engineer should definitely inspect the cores or the outcrops, get the core in a hand, scratch it, get a feel about the material. It's quite important to get to justify the numbers that we are evaluating. In any case, I would also recommend to apply the 4I principle, in particular the GSI values, because this is very subjective interpretation and it is very useful to have a second opinion. And most importantly, this applies to all geotechnical works. We need to consult a local geotechnical engineer and try to find out the experiences from comparable conditions. Once when we have all these fundamentals, we are getting into the determination of the rock mass parameters. Usually the rock mass strength and deformation moduli are estimated commonly using the Hoek-Brown criterion, which is widely accepted and applied in industry. The equation of the Hoek-Brown criterion in a first view maybe reads complicated, but in general terms it's quite simple, and it requires only a few input parameters to come up with the rock mass strength. Important when applying, and this is actually applicable for all empirical models, is to understand the application limits. I have noted here the application limits for the Hoek-Brown criterion on the lower side. For example, at this extreme low end of the rock competence, let's say the GSI value is lower than 30 and the composite strength is lower than 50 megapascals. So we are talking about a ground which is up on the lower end of this GSI chart. So the discontinuities will play a lesser role, and the rock mass itself will be governing the matrix behavior. So this is quite important to note for near-surface tunnels. Among other parameters which needs also consideration while deriving the parameters for the rock mass are definitely the virgin stress field, groundwater conditions, and most importantly, most of the people disregard this. This is the orientation and the opening of the excavation itself in relation to the rock mass structure, because you will appreciate that there is a significant difference between a rock behavior in a scale of, let's say, 15 to 16 meters wide excavation compared to a scale of 1 cubic meter of a rock, which is more or less the intact of the rock. Coming to the parameters, so most conventional computer codes are formulated in terms of the Moore-Coulomb failure criterion, and we as engineers are rather used to work with the friction angle and the cohesion than with the Hoek-Brown criterion. Some numbers are given here, so this seems for us a little bit arbitrary. And insofar we are trying to convert the parameters from Hoek-Brown to Moore-Coulomb. In converting the shear parameters, but we need to keep in mind that the Hoek-Brown criterion or the failure criterion of Hoek-Brown is a non-linear parabolic which distinguishes itself from the linear Moore-Coulomb failure criterion. Hence the failure envelope range, let's say the stress regime or the stress range, is quite decisive for the Moore-Coulomb fit. Depending on the stresses, if you are looking at lower stress regimes or higher stress regimes, the shear strength values can be different. Based on my personal experience, based also on back calculations, I can state that the Hoch criterion has its limits at the extreme lower end of the rock competence scale. I would say the shear strength, the shear stiffness, the stiffness values of the rock mass are overestimated by using Hoch criterion. So we need to be very careful in using the numbers for our designs. And now let's move on to the numerical stress and strain analysis. In the earlier slides, when we were discussing the main challenges of the project, I was mentioning that 2D and 3D competitions have been carried out. So this included continuum and discontinuum analysis. But due to the shortage of the time, I will just focus on this 2D analysis. And in here, I will highlight two particular aspects of two-dimensional numerical stress and strain analysis. On this screen, we see a zoomed section of a continuum model approach, where the excavation is simulated in by a plane strain calculations. We can see also in this cross-section that different lithological units and discrete weakness zones are modeled by means of continuum elements. Further of note is also that the various construction sequences, meaning the excavation stage, the installation of the support, has been also modeled in an accurate way in order to realistically interpret the soil structure interaction and, of course, the load shearing effect. That's quite important in analyzing in 2D. The first aspect that I would like to talk with you is about the stress release factor. Since three-dimensional arching effects of the ground will occur as we advance the tunnel, as it is schematically depicted on this diagram, we need to have an appropriate adjustment, or we need to make appropriate adjustments to capture this three-dimensional effect of the stress releases in front of the face in 2D or two-dimensional analysis. And this is usually done by the means of pre-relaxation factors. The figure on the lower right-hand side depicts this complex stress state at the tunnel face in different excavation and support stages while we are advancing the tunnel. Let me maybe quickly go through it. So in section 3, this section 3 depicts the virgin stress rate, meaning the zone which is uninfluenced by the tunneling works yet. In section in the section B, that's the situation when the tunnel is excavated, but it is not supported. The stresses around the tunnel perimeter releases to a certain amount. This is accounted by the factor B, beta. And ultimately, in section A, when the ground support is installed, only the remaining portion of the stresses are exerted to the ground support system. And the key hereby is to define the right value for the stress release factor. As you can imagine, it has a direct impact on the tunnel ground surface and also the stresses of the initial support system. So it's quite important to come up with the realistic numbers for the stress release factors when using two-dimensional analysis. There are a lot of theories where we can get a first impression or first guess for the stress release factors. Just name one or two, like the Kilbasa method or Vachapolos. But we also need to appreciate that most of them are not applicable, or I would say conditionally applicable, for shallow cover tunnel. And my recommendation would be, when we are analyzing shallow cover tunnels, to investigate the influence of varying pre-release factors. This can, as a starting point, of course, we can use the available theories, but my recommendation would be to investigate the variance of the pre-relaxation factors on the general behavior of the tunnel. So being on the safe side of the tunnel design, an upper bound value, for example, or an upper bound loading of the structural system should be analyzed, and an upper bound for the tunnel and also the ground deformations should be analyzed by assuming lower values or higher values for the pre-relaxation factors. The second aspect that I would like to share with you is the aging effect of the shotcrete. Appreciate that the shotcrete will change its stiffness and strength characteristics with the curing time. And when we are modeling the shotcrete lining, we need to distinguish between the young and the hardened shotcrete properties in order to incorporate the aging effect in an appropriate way. This will have an effect on the deformations and also the stresses in the tunnel itself. Here is an example of a result of such an analysis. The proximity of the ground surface usually means that the failure path for the rock mass surrounding the tunnel head or the tunnel ahead of the tunnel face is to cave into the surface. So, and exactly this phenomenon is depicted as a result of one of these calculations. On this result, we see the contours and the vectors of total displacement in the rock mass surrounding the busway tunnel. And as you can see from the displacements are extending right to the surface, and the direction of the displacements indicate exactly the phenomenon or the sensitivity of this caving process. The contours of the shear strain and shear trajectories on the right-hand side shows us that the arching is developed only partially for the busway tunnel, and under these circumstances, a complete arching of the rock mass above the tunnel cannot be relied upon, and the initial ground support will have to be designed to carry the adverse ground loads, which results from the assumption of instantaneous installation of pre-support. This will include canopies or spiles to secure the tunnel advance and to prevent the caving process, as it is also demonstrated here by the numerical calculations. These diagrams show a typical ground surface displacement, and we see on this diagram different curves representing different stages of the construction sequence. It's maybe very difficult to read the numbers, but maybe highlighted this way. We were hearing that first the top heading of the mainline tunnels have been excavated, followed by the heading of the busway tunnel. Once when we are opening the heading of the lower tunnels, we see that the effect on the ground surface is very minimal. There are several effects, of course. First of all, the tunnel is much deeper. Secondly, the ground in these deeper elevations are much better. But once when we are opening and excavating or supporting the heading of the shallow cover tunnel, we see there is an immediate response of the ground surface displacement. The ground surface displacements jump right away when we are opening the heading, and this shows us the sensitivity of the heading excavation. This is a different way to depict or to demonstrate the sensitivity of the ground surface displacement for near surface tunnels. In red curve, we see or the ground surface displacement are tracked at the center line of the tunnel, and in blue, the deformations, the measurable deformations of the tunnel crown are recorded, and the deformations are shown with the excavation stages. And we see during the excavation of the heading of the mainline tunnels, the deformations are moderately low, and once when we are opening up the tunnel heading, the deformations are increasing rapidly. Now the question becomes, how do we overcome the limitations of these empirical models in terms of shallow cover tunnels, in particular with relation to the stress release factors? One way would be definitely utilizing a three-dimensional numerical model. A 3D model has also its challenges, but a 3D model has actually two components. So first of all, the complex geometry can be simulated in a more realistic way as in a 2D section. And secondly, and that's the most important part, in a 3D, we no longer need the stress release factors. and hence the results of a 3D can be utilized for the verification of the stress release factors that we are using for a 2D simulation. As in the previous slides already discussed, the portal area of the Northern Busway Tunnel are situated in an area of low cover, where the cover of the tunnel is or consisting of man-made fill or loose fills, underlined by very highly weathered rock of poor quality. Hence, the 3D FE model have been developed for the portal areas to assess the complex stress state and stress redistribution, and of course to analyze the rock mass behavior upon the tunnel excavation in different stages, and to identify the critical stress rates and the possible failure mechanisms, of course. And on this slide, we see a typical model for the south portal, but due to the shortage of the time, I will not discuss the details of this 3D analysis. This would be the situation at the north portal. Out of a 3D calculation, we can obtain such results, for example, the total displacement representing the sphere that we are excavating, and you can see here, this is the POPs victory that we were discussing at the south portal area, and this would be the situation at the north portal area. So, and all these results combined from 3D analysis and 2D analysis, when we are superimposing this, they deliver us the complete picture of the displacement that we are anticipating caused by the tunnel excavations. And here on this slide, we see a typical isochron map, so practically lines of equivalent deformation values. And this kind of maps are quite useful. I would say it is constituting the basis for the building damage analysis and also the zoning plans for building damages. Yeah, on this slide, I would like to demonstrate the value of a back calculation. So we have here the difficulties with the geotechnical models, with the complexities of deriving parameters, the complexities of simulating a 3D effects in numerical calculations, etc. If we have an opportunity, we should definitely back calculate and verify our rock mass parameters. In particular, in a shallow cover tunnel, the E modulus is quite important. And this is a very complex diagram. Let me maybe summarize it in this way. We see here the comparison of predicted and measured ground surface displacement. And the green arrow shows us the calculated sediment throw, and in red the measured values. And in this comparison, we see an excellent verification of our rock mass parameters. So we were very lucky that we could calibrate our model and the rock mass parameters based on the measured values which we obtained from the mainline tunnels. And this gave us a great insight in the behavior of the rock mass in order to calibrate our numerical models, which we have utilized for the shallow cover tunnel. And I would also like to emphasize, even in a rock mass, we are able to simulate the deformations quite realistically, even utilizing the Moore-Coulomb failure criterion. Now, I would like to share a few construction impressions. So that's the POPs victory. I can tell the construction has been completed and the POPs victory survived all the construction works. We see the construction works at the tunnel face. This is the starting of the tunnel at the south portal. So this is more advanced in the tunnel. So we see the canopy tubes and some works at the face. We can also see some face bolts at the face. This is a detail where a rotor is excavating the NFG material. We see here double layers of mesh supported by shot crates, and also indicated here the canopy tubes. So these are some details of the work from waterproofing. An interesting detail is the niches, which constitutes quite often effort to make sure that these are not the leaking points. So this would be the final lining, the final product of the tunnel. Yeah, coming to the conclusions. I hope you can take away 3 points from this presentation in regards to the near surface tunnel aspects. Let me summarize it. The rock mass parameters, in regards to these parameters, so the Hoch-bound criterion is conditionally applicable, and my recommendation would be continuous calibration of the geotechnical model, but also the rock mass parameters. If we have any measured values from tunnel excavations, this will give us a much better prediction. In particular, the E modulus is quite often important for the rock mass when it comes to the deformations of shallow cover tunnels. When simulating in 2D, the pre-release factors are quite of importance, and we just heard that the classical convergence confinement methods are not applicable or only conditionally applicable. And in here, my suggestion would be to run a 3D FE analysis or run sensitivity analysis to evaluate the effect on the deformations and on the structural forces in the lining or the anchors. Also of an importance, the rock cover to span ratio. So we were successfully to give this criteria. So the criteria is if we have an cover to span ratio less than 0.45, then we need a passive support. With that I'm meaning, so we need to take the rock loads by the shot grade shell. An active support would be dealing with the stresses and the deformations by, let's say, by rock bolts. Yeah, thank you for your attention. I trust we have some minutes for question and answers. But should we, yeah,
I was going to say, sorry, go ahead. We certainly do have time for some questions.
Perfect. Yeah, but should we still run out of time? So my contacts are given here, and I would be happy to answer your questions by email.
Thank you so much for that detailed presentation, Tanner. That was wonderful. We do have questions coming in, and I'd like to invite attendees to please submit questions via the chat panel. We'll go ahead and read them off so we can capture them in today's recording. The first question reads, it's a two-part question. Why were the airport tunnels excavated before the busway tunnel? Was it scheduled or ground conditions to dictate the order?
It was dictated by the schedule.
Excellent. The next question reads, did the client request a 3D model or did you persuade them of its value?
So it was just for us to have a better understanding of the ground deformations or the reactions. And so basically it was our decision to support our two-dimensional analysis by 3D.
Great. Another question, will you be presenting at the WTC, the World Tunnel Congress in San Francisco this year?
Yes, partially, but it will not be, the topic will be a little bit different. So this will be a project that we were working on in London, and the general topic would cover TBM. And of course, on this project, it will be also a low cover, but related to TBM excavation.
Wonderful, thank you. I'd like to also remind attendees today, today's session was recorded, and we will share this recording on the UCA Young Members website. And we will also have the updated information for next month's webinar that should be held on March 30th. The last Wednesday of the month is when we hold our UCA Young Members webinars, and we hope you can join us for that. Tanner, at this time, that seems to be the last of our questions. Would you like to make any closing statements?
Yeah, closing statements, maybe because this is more or less addressed to young members, and I would just emphasize the importance of the geotechnical modeling. And there are a lot of uncertainties related to the input parameters. It requires a lot of understanding when we are deriving the parameters. And more importantly, and that's quite important to me to emphasize, when we are utilizing numerical models, it is quite easy to come up with the geometry and put in some numbers and come up with some colorful, let's say, results. The difficulty is really to understand the behavior that we would anticipate in a real case situation and to try to come up with solutions or simulate the realistic behavior. That's quite important.
Wonderful. Thank you so much. That looks like that is it for our questions for today. So everybody, thank you again for joining us today, and we hope to see you next month. And keep an eye out in the next day or so. We'll send out that email with the recording of today's session.
Yeah, thank you for listening to me and giving the opportunity to present this project.
Of course. Thank you so much for your time.
Thank you. Ciao.
All right, everybody. Have a great day.